Excellent. Very good. Did you get my email yesterday?
Yes, ma'am. I seen it kind of late because I had to go to practice.
That's fine. That's fine. As long as you'll be able to catch up without too much trouble. And I put you in the group for the group quiz today, so you should be all set. What's that?
I said it.
It's on my website. You just download it. All right. Is everyone ready for some chemistry excitement? Hopefully everybody's ready. All right, so our announcements. I think just about everybody has figured out mastering chemistry. As of this morning, I had 60 of the 64 signed up. Good. If you're still having technical issues, let me know and we can work something out. But I'm guessing it's probably you chose the wrong textbook amongst the 18 choices of TRO. So if that's the case, then we can work something out. Let's see, mastering, there is a group quiz today. I'll put up the group list again here in a minute just to remind you who's in your group. And then as you're thinking ahead over your Labor Day weekend, obviously we don't have class in here on Monday, but your next homework is already open, and it is Chapter 2, some introductory stuff to Chapter 2, so you can certainly work ahead on some of that homework. Bless you, bless you. Any questions before we get started? All right. In that case, we'll finish up Chapter 1 and we'll start Chapter 2 today. So this is just our definitions. I'm assuming most people have seen this in high school, right? Accuracy versus precision with the dartboard analogy, right? So accuracy is how close a measurement is to a true value, where precision is how close your measurements are to each other. So if I was a world champion dart player, which I'm not, I'm like one level below world champion, whatever that is, intercontinental title holder maybe, I would have all my darts all at the 100 points. It's obviously not a really dartboard because it would have to have the things going up to the side because you can't play cricket if you have this kind of dartboard. Anyone actually play darts in here? No. In that case, this analogy, those were hilarious jokes that don't make any sense to you. So just roll with it. All right, so you have your 100 points, right? If you were great, you would have all the darts right in the center. If you were not a good dart player, but pretty accurate in your throws, you would have them all clustered together. So that's precise but not accurate. If you were terrible, which apparently most of you guys would be because you don't play darts, this would be what your dartboard would look like. And to be honest, it probably wouldn't even, it would probably be over here, way over there, all off the dartboard into the wall, right? So that would be not accurate and not precise, and you would not be on my team. I would choose someone else to play with me. Good? All right. In that case, let's talk about unit conversions. If you have a calculator with you, go ahead and fish it out because we're going to be using it. If you don't, no big deal. Apparently, I have a whole box of spares. Does anyone want to borrow a calculator? Oh, very good. All right, unit conversions. So in many cases throughout our study of the wonderful world that is chemistry, we are going to have units that are in one form that we need to get to units of another form. And we have to make sure that we answer the question in both a numerical answer and the correct units. Otherwise, we are the satellite that is lost in the universe. That's a big, profound thought. Think about that. All right, so let's say let's see, do I want to do this on this slide or this slide? I'll do it over here. All right, so we're going to use unit conversions to get from one set of units into another set of units. So you guys are probably familiar with this, right? How many people have ever driven in Canada? Been to Canada? Been to a country that uses metric? All right, good. Okay, that's at least a few people. So take this back. Imagine your speedometer, right? So picture your speedometer. If you have an old version of the speedometer, right, you have miles per hour on the top, you have kilometers per hour on the bottom. We're going to be doing things like that where we want to convert our speed from what we're familiar with in miles per hour into kilometers per hour. So it's a method of unit conversion to get from one into the other. So how we do this is through the use of conversion factors, which are standard units of measurement that help us relate two units to each other. Only the units change. It's a little off focus, isn't it? That's better. And conversion factors are numerically equal to 1. So in my example here, right, 1 liter is 1,000 cubic centimeters, which is the same as saying 1,000 cubic centimeters per 1,000 cubic centimeters, which would make it 1. So, the method uses, ooh, bless you. Whew, I'm going to get you all a Kleenex or something. It's very sneezy in here every morning. Oh, it's catchy. All right, the method uses the idea that units can be canceled out if they are on. If they're on opposite sides of a fraction. So it looks something like this. In my example here, where I have a liter per 1,000 cubic centimeters, I can cancel out these cubic centimeters with those cubic centimeters because they're on opposite sides of a fraction, right? I can cancel out a numerator with a denominator. So in words, we can say if I do a given unit times a fraction that has my desired unit over given unit, the given units would cancel, and then I'd be left in the units I want to end up in. So we're going to do some basic practice about how to do some in general conversions. I'm going to start off with an easy problem before I go on to the next slide. So let's do this. Let's pick, we'll go to Costa Rica. All right, so let's say we're all going to Costa Rica. Yay. But the issue is I only have American dollars. They don't take American dollars there. They take the cologne. So I need to go to one of those money exchanger places and figure out my money situation. Currently, $1 gets you about 504. The exchange rate's really good in our favor. So if you travel to Costa Rica, you're going to be making out like a bandit. So that's about the exchange rate as of today. I have on my body $125. I go to the exchange place. How many cologne should I get back in return for that? So, using our snazzy method listed up here, the units we are given are dollars, right? And these are the units I want. It's beyond want. I desire these units. So like want would be nice. We desire, one step above wanting these units. Hopefully that encourages you to do it right. So that means I have 125. Is everyone okay if I don't put the little multiplication thing or the little dot, if I just put the two things together and use the same thing? Sometimes I remember to put the multiplication dot. Sometimes I forget. So if I want the dollar signs to cancel out, do I put the dollar signs on top of my fraction or on the bottom of my fraction? I want them on the bottom. So I'll put $1 down here, 504 up here. How many should I get for that? Good so far? Good little warm-up. So in general, what you're going to do for all these kinds of problems is you are going to identify the given unit, identify the desired unit, and then make a plan so that they cancel out and you end up with the one you want. So let's do some more. We'll do these three. And you can work ahead if you feel confident. We're going to go slow. All right, so let's say I have 1 milligram, and I want to convert my milligrams to picograms, knowing that 1 gram is 1 times 10 to the 12th picograms. So there's actually a double conversion unit problem. All right, so, right, these are my given units. These are the ones I want. But the conversion factor I was given is in grams. So you have to do a two-stepper. Figure you guys were ready for 2 steps. So here I have, where do I want to put those milligrams so that they cancel out, top or bottom of my fraction? All right, we're going to want to put them on the bottom. Now I need to use this, so I know it has to be grams on top. How many milligrams are in 1 gram? 1,000. If you don't know that yet, that's all right. You'll know it hopefully by the time I see you back next Wednesday. All right, so good. Good first step. Am I done? No, because I'm not in picograms yet. I want to get rid of those grams. So where am I going to put the grams in my new fraction? On the bottom. I'm going to get rid of them. And then what do I put on the top to tell me about picograms? This number right here, right? All right, we ready to calculate? Okay. Now, depending on your calculator, you can put this in a few different ways. So if you're having trouble getting the scientific notation on your calculator correct, just let me know after class and I'll show you how to put it in based on your model. Let's see here, 2, 4, 6. Or your calculator may say, or it may say, depends on which version you have. What is wrong with my answer that I would mark you off for? It's missing its units. No units, meaningless number. Good? All right, that was a good warm-up. We'll do the slightly more challenging problem. Actually, this is way easier. Number 1's harder. Number 2's easy. Number 3. 3's my tricky one. All right, let's say we've all moved to England and we're at the doctor's office. And the doctor you're using in England is going to weigh you in stones, where 1 stone is 14 pounds. How much when you're converting back in your head, how much do you actually weigh if you weigh 11.29 stone? So first we have to figure out which one is the given unit. Stones, right? I was given stones, so I'm going to start off with that. What do I want to end up in? I want to end up in pounds. So do I put the stones on the top or the bottom of my new fraction? Let me know if I'm going off the bottom of the screen or can't see it, because obviously I'm never looking behind me. All right, so I got 1 stone for 14 pounds. Cancel, cancel. So let's see, 11.29 times 14. If you're thinking about sig figs, what's kind of funky about this answer? Yeah, it's not the great sig figs, which you're going to spend all lab next week working on. But I started off with 4 sig figs. This is considered exact. So all conversion factors are exact and do not count when you're thinking about significant figures. So that's a helpful tip. Conversion factors don't count. So it just matters how many digits you put in to how many digits you get out. To be more accurate to say, if you're not feeling confident on your sig figs, that's all right. We're going to do a bunch more. The rules are kind of tricky sometimes. All right, last one. We're ready for a challenge problem. How large is Australia in square meters if I know 1 mile is 1,609.34 meters and my land mass is real close to 3 million square miles? So what units am I given to start off with? Square miles, right? All right, so miles squared. can I cancel out some of those units? Am I given anything that converts square miles to square meters?
Yeah, 1 mile.
1 mile is 1 meter, but I need square miles.
So don't you just square it?
Sort of. I think it's easier if you do it this way. My parentheses is too small. Okay, so what are my new units on the bottom here? Miles square, so now I can cancel those out. Let's see, what does that turn out to be? 7.61, 4, 10, 12. Yeah. What would be my new units in that? Okay. All right, does everyone feel fairly confident in those, like some basic, get us started unit conversions? We do a lot of unit conversions in here, so this is just kind of some warm-up practice. Okay, I am going to come back to this problem. Problems with equations. We're going to do some other stuff and we'll come back to it. So I'm not forgetting about it. We'll come back. All right, so let's talk about some more theoretical chemistry in that it doesn't have exact numerical values. Atoms and elements. So let's talk about the atom and some general atomic theory, which again is going to be a lot of stuff that you're probably fairly familiar with. Right, so if I take an element, a sample of elements, the element is composed of atoms, and all the atoms of a same element all have the same chemical properties, right? So if I take a bunch of iron from one place and a bunch of iron from another place, they're all made up of iron atoms, and they all will behave the same. If I then, bless you, combine atoms of different elements, they behave differently, right? So let's say I have H2O versus O2 versus H2. Which of those is a compound? Right, H2O is a compound because it has two different types of atoms combining together. It has some H's, has some O's working together. What then must oxygen or hydrogen be? Right, those guys are just elements. Because they are all the same type of atom stuck together. So when we do a chemical reaction, what we're doing is we're either going to separate out atoms, we're going to rearrange them, or we're going to combine them in a slightly different way than the way they came in. So there are 3 laws that govern how we can separate, combine, or rearrange atoms. Three fundamental laws. conservation of mass, the law of constant composition, and the law of multiple proportions. I'm guessing that just about everybody's at least familiar with the first one. That one's like a go-to science law. The other two, maybe not. They're a little more conceptual. So in our law of conservation of mass, we have that matter is neither created nor destroyed in a chemical reaction. We'll do just the broad definitions first, and then we'll kind of dig into some examples of these. In the law of constant composition, all samples of a compound have the same proportion of elements. And the law of multiple proportions has when you combine elements to make compounds, they always combine in a ratio of whole numbers. All right, so like I was saying, the first one, pretty straightforward. These other two will take us a little bit of time to kind of dig through what exactly that seemingly ambiguous statement is telling us. So let's do the first one first, because that's the easiest, and plus it's first, which means you have to do it first, right? First is first. Let me know if I'm moving the sheets too fast. I tried to slide them up. All right, so then the law of conservation of mass, right? Matter is neither created nor destroyed. So if I have here I have some sodium metal and some chlorine gas. I have 7.7 grams of sodium and 11.9 grams of chlorine, which means the total mass is 19.6 between those two items. If I was somehow able to squish them together with my bare hands to make sodium chloride, I would make 19.9 grams of sodium chloride. All right, so I didn't make any new mass, I didn't lose any mass. As much mass I put in is how much mass I'm going to get out. So if I have this other example, let's say I have okay. All right, so let's say I have 10 grams of fluorine gas and 6.2 grams of chlorine gas. What altogether mass do I have to start off my reaction with? You can use your calculator if you need to. 16.2, excellent, okay. All right, so we have 16.2 grams going in. How much mass should I get coming out? It's like you guys have used this law before. Yes. You will make Good. Hopefully that was a confidence builder. You feel pretty strong about numbers in equals numbers out. Good. All right, in that case, you're now experts at the law of conservation of mass. So let's do the two other ones that are maybe not quite so straightforward. So the neat thing about chemistry is that is considered a new science. I mean, really, the biggest chemistry inventions have happened really in the past 100 to 150 years, and it's still changing. And so in 1797, Joseph Proust noticed that when he had elements of a given compound, they were always combined in the same ratio, which was mind-blowing at the time. So, for example, we'll do a generic example. Let's say I have a sample of H2O and you have a sample of H2O. Right? We both have water. All of my water is 2 H's to 1 O, and all of your water is 2 H's to 1 O. In 1800, that was unheard of. That was crazy talk. They thought that just atoms combined randomly to make random chemicals, and they had no idea that it was always the same proportion for everything. So, if we look at the experiment he in particular did, he had 17 grams of ammonia. Decomposed. It made, let's see, what's a good, let me double check my math. This is looking a little funny. Hold on. Right, so we saw the law of conservation of matter, right? He put in 17 grams, and he got out 14 grams of nitrogen and 3 grams of hydrogen. Every time he did this, he always got 14 grams and 3 grams. So he was saying that every time it combined, it was 1 nitrogen to 3 hydrogens. So that's the definite proportions rule. It's just, if you have a compound, they will if this is ammonia, it's always going to be 3 H's to 1 N. If it's water, it's always going to be 2 H's to 1 O. If it's hydrogen peroxide, it's always going to be 2 H's to 2 O's. Okay? All right, then let's talk about multiple proportions. So let's say I have 2 different elements, A and B, just for generic sake. They can form different compounds depending on which ratio they combine together with. So it's very wordy, but it means so here I have 2 hydrogens for 1 oxygen versus 2 hydrogens for 2 oxygens. Right, so they're both made of just hydrogens and just oxygens. But if I want water, it'll always be 2 hydrogens to 1 oxygen. If I make hydrogen peroxide, it'll always be 2 to 2. So it's saying I can combine H's and O's in a few different ways to make different compounds. And the ratio of element A to element B will always be a whole number. Right, so this is saying I have 2 H's to 1 O, this is 2 H's to 2 O's. I can't have 3 H's to 1.5 O's. Right, they always have to be whole number combinations. I think I can come up with a different example. All right, that's another good example. CO versus CO2. All right, carbon monoxide, carbon dioxide. So that carbon monoxide is the one that definitely will kill you. Carbon monoxide is still not great for you, but definitely different in properties. Both gases, but. All right, we'll do one last topic, then I'll let you guys have your 10 minutes to take your quiz. Let's at least start a little bit. It sounds scary. It's not. Atomic theory. And what's crazy is that it's still a theory. Like the 3 last things we just did were laws. The atom is still theoretical. We're still not 100% sure what's going on there. So we don't have any way to exactly measure what's going on. So even though we consider this fairly basic now, let's think about that too. You guys are all learning this as like your intro to chemistry course. 100 years ago, this was purely theoretical. Einstein was trying to figure out what was going on at the atom level. It was hugely controversial. And now we're like so obvious that we teach it in our intro course in the first week of classes. So, science, come a long way in just 100 years. So, Dalton explained those 3 laws, and he combined it with his version of the atomic theory, which states 4 parts. 1. Right, that seems fairly obvious now. 100 years ago, super controversial. Each element is made of atoms. All atoms of the same element should be identical. Atoms combined together in only whole number ratios. And finally, atoms of one type cannot spontaneously become atoms of another type. Right? You can't have an atom of iron floating around being, you know what? Not feeling it. Think maybe calcium. Calcium. Not possible. We can do some crazy chemistry to force elements to change. Nuclear reactions, we can force uranium to break apart, become something else, but you got to put a lot of work to make that happen. Spontaneously, they can't just be floating around being like, You know, I'm feeling like a magnesium today. Magnesium. So, not possible. All right, so we will stop there, leave you on a cliffhanger about, man, what is in an atom? I'll give you some spoilers. Proton, electron, neutron. Think about that. So if you don't remember from the other day who your group was, I think this is everybody in the class. Does everybody see their name on there, hopefully? If you know who's in your group, go ahead and you guys are also move close to the other group members in some way. Either all sit in one row or sit back to back, whichever way works out best. If you don't know who your group members are, raise your hand and I'll do my best to help you find them. Oh man, half the class. All right. Let's see. Which, I don't know everybody's name yet. Betsy. Let me find it. Yeah, you're done. Yeah. Let's see. All right, so Betsy is looking for Charles, Sarah, and Emily. These people. Are any of these people around? If so, Betsy's up here in the front. Good, good. All right, who else is looking for their group? Tell me your name again. Austin, all right. So you're sitting right there with Jalen. And then you're looking, Samantha's right there. Good, and is Savannah here? I will go ahead and lead her then. Fair enough. All right, next is just a group of 3. Good. All right, who else is looking? Tell me your name. Abigail. Oh, here you are. All right, so with him, Michaela. Oh, you two are with her and him. So if you guys want to move to the back, that'd be good. All right. Oh yeah, totally fine.
Is this true?
Yeah. Your left, my left. Oh, okay. So you're looking for Jordan. Is Jordan here? Jordan, okay. Is Eric here? Oh, is Taylor here? Oh. All right. For sure you're with Marie then. All right. Cameron, let's see here. All right, so Sabrina. Oh, right there. There they are. All right, has everybody mostly found their groups? All right, so let me give you some quick instructions. On group quiz day, I give a quiz to everyone in your group. I only want one copy back that has everybody's name on it. Everybody else gets to take theirs home. The person who turned theirs in will get it back next time I see you. So everybody will get it back eventually. It's just take the one that has the nicest handwriting. So as you're deciding who's to turn in, make it the one that I can actually read. Yeah, any way you want. You can do it individually and share answers. You can do it all together.
We've got all of our names on one sheet.
Yes, whichever person turns it in, make sure you have all the names on it. So I can give you this or